Hello and welcome back to Hands-on Machine Learning with PyTorch. In our journey so far, we've tackled several foundational projects, from linear model to custom CNNs, gradually building up the skills to work with real-world deep learning problems. Today, we're taking things a step further by diving into the world of transfer learning, a powerful technique where we use the pre-trained deep learning model and adapt it to a new task. Our focus, the Sign Language MNIST dataset, a collection of hand gesture images representing American Sign Language letters. And for the model, we'll be using ResNet18, one of the most powerful and effective convolutional architectures pre-trained on ImageNet. In this tutorial, we'll walk through the entire process, exploring and visualizing the dataset, pre-processing and preparing a custom PyTorch dataset, fine-tuning the ResNet model for sign language classification, and evaluating the model performance. This project will give you hands-on experience with transfer learning, image preprocessing, and real-time inference, all using PyTorch. So, if you're ready to take your computer vision skills up a notch, let's dive in and start building a powerful sign language recognizer from scratch. We'll begin by setting up our environment with all the necessary variables. We'll start with PyTorch and Torch Vision, which gives us the tools to build and train deep learning models and work with image transformations. We'll also bring in pandas and numpy for data manipulation and PIL to handle image conversions. For visualization and analysis, we'll use Matplotlib and Seaborn, great libraries for plotting things like training curves and confusion matrices. And finally, we'll import tools from scikit-learn to help with data splitting and model validation like classification reports and confusion matrices like we did in our earlier videos. With these libraries in place, we're fully equipped to load, explore, process, train, and evaluate our sign language model. Now let's move on to loading the dataset and building our custom PyTorch dataset class. Before moving on to building our custom dataset class, let's set a few configuration parameters that will guide our training process. We'll define a batch size of 64, which means the model will process 64 images at a time during training. This helps balance memory efficiency and learning stability. Next, we specify 5 epochs, meaning the model will see the entire training data 5 times. You can always increase this later if you want better performance. Finally, we determine the device. If a CUDA-enabled GPU is available, we'll use it to accelerate training, otherwise it will fall back to the CPU. This line ensures that our code is hardware agnostic and can run smoothly on any machine. With the configuration in place, let's now create a custom dataset class to handle the Sign Language MNIST data. Now we'll get our dataset ready for training. We start by creating a custom dataset class called Sign Language Dataset, which extends PyTorch's built-in dataset class. This class lets us define how to read and process each sample from our dataset. Inside the constructor init function, we pass in a data frame and an optional transform. This data frame is just a CSV file where each row contains the labels followed by pixel values of an image. In the len method, we simply return the number of samples, a required step for any PyTorch dataset. Then in getItem method, we extract a sample by its index. The label is in the first column and the rest of the row contains the image data, which we reshape into a 28 by 28 image. Since the pixel values are all integers, we convert them into a proper image using PIL. If a transform is specified, we apply it here. This will be important for resizing and normalizing the images for ResNet. Next, we load the dataset from Sign Language MNIST CSV files, one for training and one for validation. These files contain hand gestures labeled from A to Y, excluding J. To make our training more robust, we split the original training data into training and validation set using stratification to preserve class balance. Then we define a transform pipeline using transforms.compose. Here's what the transform does. First, we resize the image into 224 into 224 pixels, which is the required input size for ResNet. Then we convert grayscale images into 3-channel format because pre-trained ResNet expects 3 color channels. We convert the PIL image into a PyTorch tensor. And finally, we normalize the tensor to have values between -1 and 1 using a mean and standard deviation of 0.5 for all 3 channels. This pre-processing ensures our custom grayscale data can be used with a powerful pre-trained model like ResNet. Next, we'll use this dataset class to create data loaders for training, validation, and testing. Now it's time to wrap our data into PyTorch data loader objects. We begin by creating three datasets: train, val, and test, each an instance of our Sign Language Dataset class. We pass the respective data frames along with the transform pipeline to ensure all images are processed in the same way. Once the datasets are ready, we create data loader for efficient data handling during training and evaluation. The train loader is where we'll load batches of training data. We also enable shuffling to ensure the model doesn't learn the order of the samples. The val and test loader are used for validation and testing. Here, we don't shuffle the data since our order doesn't impact evaluation. These data loaders will help us feed data to the model in mini batches, optimize GPU usage, and keep our training loop clean and scalable. Now comes the heart of our transfer learning setup, loading a pre-trained ResNet18 model. We're using ResNet, a well-known convolutional neural network that's been pre-trained on ImageNet, a massive dataset of over 1 million images. This gives the model a strong foundation of learned visual features such as edges and shapes. We then modify the final layer of the network. By default, ResNet18 is designed to classify 1000 classes from ImageNet, but our Sign Language MNIST dataset only have 25 classes representing the letters A to Y excluding Z. So we replace the final fully connected layer with a new one that outputs 25 logits, one for each class. Finally, we move the entire model to our competition device, either a GPU if available or fall back to CPU. With our model architecture now ready for training, we'll move on to defining the loss function and optimizer. To train our model effectively, we need to define two key components, the loss function and the optimizer. For this multi-class classification task, we are using cross-entropy loss, which is the standard choice when working with classification problem. It measures how far our model's prediction are from the actual labels, and the goal is to minimize this value over time. Next, we use the Adam optimizer, a popular choice for deep learning models. Adam combines the advantages of two other extensions of stochastic gradient descent, AdaGrad and RMSProp, and adapts the learning rate during training for each parameter individually. We've set a learning rate of 0.0003, which usually works well when fine-tuning pre-trained models. Together, these choices help our model converse faster and more accurately as it learns to interpret sign language gestures. Now it's time to train our model. We begin by setting the model to training mode using model.train function. This enables certain layers like dropout and batch normalization to behave appropriately during training. Next, we iterate over our dataset for a number of epochs. In this case, 5 full passes through the training data. Inside each epoch, we loop through batches of images and labels. Each image and its corresponding label is sent to the appropriate device, either a GPU if available or the CPU. Before making a prediction, we call optimizer.zeroGrad to clear out any gradients from the previous step. Then we pass the images through the model to get the output predictions. We calculate the loss between the predicted labels and the true labels using our defined loss function. Calling loss.backward computes the gradients, and optimizer.step updates the model's weights. Now we keep track of the loss across all the batches and point out the average loss at the end of each epoch to monitor training progress. This loop is where the model learns, gradually adjusting its internal parameters to become better at classifying sign language images. With training complete, it's time to evaluate how well our model performs on unseen data. We start by setting the model to evaluation mode using model.eval. This disables layers like dropout and ensures consistent behavior during inference. We also use torch.nograd to turn off gradient tracking, which helps us save memory and computation since we are not updating weights during evaluation. As we loop through the test data, we move the images to the correct device, making predictions using our trained model, and use torch.max to identify the class with the highest probability for each input image. The predicted labels and true labels are collected into separate lists for further analysis. Next, we generate a classification report which gives us precision, recall, and F1 score for each class. This is useful for understanding how well the model performs across different sign gestures. Finally, we visualize the confusion matrix using a heat map. This gives us a clear picture of whether the model is making correct predictions and whether it might be getting confused between similar gestures. So this block gives us both numerical and visual insights into the model performances on real data. And that brings us to the end of this hands-on project on transfer learning using ResNet for sign language classification. In this video, we saw how to take a powerful pre-trained model like ResNet, adapt it to our custom dataset, in this case the Sign Language MNIST, and train it to recognize 25 different hand gestures representing the alphabets. We walked through the entire pipeline from dataset exploration and preprocessing, building custom PyTorch datasets, setting up data loaders, modifying the model's output layer, to training and evaluating our model. Although we started with a model trained on natural images, we were able to fine-tune it to understand grayscale gesture images with just a few epochs, demonstrating the power and flexibility of transfer learning. This approach not only saves time and computational resources, but it also opens the door to building robust models even when working with relatively smaller dataset. So, if you found this video helpful, make sure to like, share and subscribe. And I'll see you in the next one where we take deep learning a step further into the real world.